I I suppose I could stay up at that late. James Clerk Maxwell on being told on his arrival at Cambridge University that there would be a compulsory 6 a.m. church service. So the next protocol that people are excited to be able to find is the last, final cork, the one that sits underneath the up cork and the charm cork, the one with a charge of the two straws. That would be what we would call the top cork, and everybody expects it. So this is, 1977, but everybody also expects that it should be heavier than the bottom cork, and nobody knows exactly what its mass should be. I want to remind you that the theory of quantum chromodynamics is a rigorous mathematical framework. You can make a calculation of almost anything. Wow. But I mean, that's why you can find out it, right? But it's a renormalizable quantum field theory. That's a fancy word that means that there is some infinities that arise mathematically, and to fix them, there is a couple of things that you cannot compute. One of those couple of things is the mass of the fundamental particles themselves. You just can't predict that from the theory. So you can't predict from the QCD what the mass of the top cork is going to be. You can make some educated guesses. Not by looking at the fundamental theory, but by looking at the data. Okay, how do I mean that? I mentioned in the previous lecture that the people already had an idea for the mass of the charm cork by considering events where our charm cork might appear virtually, very briefly, and then disappear again, right? The fact that it's real and it exists in nature means that you can sort of create a charm cork out of nothing if you give it back again, even if you don't have enough energy to actually make one come free. And the pulling of the little charm cork or any cork out of the vacuum affects observables. Even if you just scatter an electron against another electron and you look at the probability of them going off at some particular angle. If you calculate that with the Feynman diagrams, you must include every possible intermediate states, every possible splitting of the vacuum into the particle, antiparticle, and then they will change the probability a little bit. So this is called precision particle physics. If you make a super precise measurement and then you make a very careful calculation, you can compare the measurements with the calculations, and you might be able to deduce the mass of this one last unknown cork, the top cork, by calculating the effects of, well, if it's there, then we should be able to produce a virtual top, anti-top. And if we do that, it's going to change any observable that you can think of, but by a very small amount. So this was big business. Starting in the 1977, people were looking at all of the data that they had, and at first it was very crude. People said, well, it's probably more than the hundreds giga electron volt and probably less than the thousands. It was that loose. As the years went by, I would go to conferences and there was always a series of talks. The status of the standard model, and one of the things that they would always talk about is, okay, we've done these calculations and we are honing in. And I remember it was between 150 and 1200 giga electron volt, and then between 160 and 880 giga electron volt. And this is now getting into the 1990s. I've gone through the graduate school, and the standard model is now taught to graduate students. It's accepted. It's accepted pedagogy at this point. It's in textbook, and you'll see a table of all the quarks and all the leptons with their masses. And then you get to the top quark, and there is a simple little question mark next to its mass. There is no questioning of the model. Well, not much. but it's just assumed that this particle's got to be there, and we just don't know quite where it is yet. It was not until 1995 that the top quark was found, so that's a long time, almost 20 years, between the discoveries of the bottom and the discoveries of the top. And yet, throughout that whole time, I think the physics community was not worried about it. We were beginning to expect where it should be based on our precision measurements of the unrelated experiments. Right. It was finally found at the Fermi Lab once again. In the intervening years, Fermi Lab had been upgraded in energy. It's now called the Tevatron. Wow. Tevatron. Because tera electron volt is an acronym for trillion or tera electron volts. So we've gone from the billions to trillions now. Wow. The Tevatron now takes protons and antiprotons, accelerates them in this the giant 4-mile ring and smashes them into one another. And so now you have the matter-antimatter annihilation of the proton with the antiproton and huge amount of energy. A trillion volt collision. And that's the energy that's required to produce these ultra-massive top quarks and anti-top quarks. I remember in 1994 there was a colloquium at my institution. Some folks from the Fermi Lab were claiming the first evidence for a top quark, so it was once again kind of analogous to the discovery of the J-psi, this time at Stanford, where you had a matter-antimatter producing a particle and then you look at what comes out. They had a few events that were consistent with what you would expect if you produced a anti-top particle. And I remember playing my role as a physicist and being skeptical. I thought, well, it's a few events. Maybe they are tossing the coin enough times, and there is another thing that makes you nervous. Remember that these precision experiments have been homing in. We expect to find a particle somewhere between 160 and 180 giga-electron volt, and what they are claiming now is a particle at 170. That was the first evidence of the top quark, and I'm thinking, yeah, maybe they are finding what they want to find. And I think that's the right attitude. They needed to convince us, and they knew that too. It took another year of the data collection before the folks of the Fermi Lab would go from announcing hints of their discovery to actually writing a paper in which they discovered the top quark. So that's a sort of a part of the sociology of physics today. People are very much aware of the statistical nature of the quantum mechanics, and there are criteria that you must satisfy. It's like tossing that coin. Getting 6 heads in a row is definitely not going to be proof that a coin is unfair. It has to be repeatable. You have to be able to leave it and come back. It has to be discovered at other accelerator facilities. Wow. The top quark requires so much energy to find that it's very difficult to duplicate this experiment, and it's duplicated in a very interesting way. Let me tell you a little bit more about the sociology of the modern particle physics. Okay, this is a huge machine. If you ever get to visit Fermi Lab or SLAC or any of these facilities, you've got to go. They are impressive machines, gigantic in scale. You walk into the area where the particle and particle collide, and there is a detectors the size of the buildings all around the region, and there are teams of the physicists. We are now talking about 500 physicists working together on the discovery of the top quark. When they publish the paper, they give you the name of the collaboration. This was a CDF collaboration and another group, the D0 collaboration. Each of them had 500 names, so the next 2 pages of the paper just list everybody's names. Wow! And there are all PhD physicists. Wow! or a graduate student and some technicians who are working essentially full-time together. It's quite a spectacular collaborative effort, and it's also extremely international. People from throughout the world works on these big projects. You know, physicists, some of them have rather big egos, so you can imagine what it's like to try to get 500 people to work together, and everybody has to agree before you can publish this paper. So, you know, you really have to have extraordinary convincing evidence before these things get published. And it's quite spectacular that not only does it work, it really works very well. At Fermilab, you've got these two beams counter-rotating. The protons go one way and antiprotons go the other way, and you have to get the beams very narrow. It's very high-tech, and then you have to make them run one into the other. Now, even though they are matter and antimatter, they are still quantum mechanical particles, and so they have a probability of interacting, but it's not 100%. Some of them will interact, and some of them will pass on by and continue to rotate. So what they do is really design the rings so they are slightly off kilter. So most of the time the protons and antiprotons just pass by one another. And there are a couple of spots around the ring where they cross paths, and those are the interaction regions, and that's where you set up your detectors. There were two major detectors at the Fermilab ring. CDF and D0 were the name of the collaborations working to search for the top quark, and they were completely independent. It's like two teams and they are fighting each other. Everybody wants to be first. If you are the first, you get the credit and the glory. You get to name it and everything, and you talk to each other. But you definitely have an independent apparatus, completely independent ideas about what would be the best way to find the top quark, right? What sort of the detectors do you build? So these experiments really are independent, even though they are occupying at the same facility and highly competitive. Both of them in fact came up with data, and in the end, the two publications agrees within the experimental uncertainties on the mass of the top quark. Again, nice confirming evidence that what we are finding is not just a wishful thinking. Today, what's the story now? We've passed through what you might call this golden age, and it's really now a period of consolidation. The top quark, and in fact the tau neutrino, was really the last. It came after 1995. It was a final discovery which really classified and consolidated the theory of strong interactions. The particles, we believe we know what they are. We think we have a complete list. At least there is no hint of any evidence whatsoever that there is a fourth generation, another new quark or lepton. It's an interesting question to ask. Could there be? You might say, well, maybe we just haven't built a high enough energy machine, and there are physicists who want to build high energy machines still. But there is not even a clue right now, not even a hint that there should be another generation. In fact, there are even some hints that there might not be another generation. That hint has to do with the neutrinos. We'll come back and talk about neutrinos in the future lectures some more. But basically, although it's hard to detect neutrinos, you can actually at least learn about their existence, because it's not so hard to produce neutrinos in certain events, and the neutrinos, unlike everybody else, are extremely light. So even though everybody else is getting heavier and heavier, we are guessing that a neutrino in a fourth generation will be light. And if it was there, we would have already had evidence for it at Stanford and in the European accelerators and at Fermilab. So there are even hints that there really isn't another generation. maybe we really do know the fundamental building blocks of the world we live in. It's a lovely and compelling idea. We also have a theory, quantum chromodynamics, which allow us to compute the properties of the top anti-top pair. What are they going to decay into? What do you expect for the behavior of the system? Everything is fitting, everything is working well. We continue to discover new particles in the accelerators, but they are not exotic. Maybe we find a charm quark paired with an anti-bottom quark. That's something new, but we expect it. We know where to look for it, and so people continuing to look to kind of verify this model. It's very important that if you have a theory, you have to look for cracks and breaks and see if there is anything wrong with it. But so far so good. We really do seem to have a well-established framework for understanding the world. Now, we have 6 fundamental quarks, up and down, charmed and strange, top and bottom, and we have 6 fundamental leptons, electron and electron neutrino, and muon and its neutrino, tau and its neutrino. That's a lot of fundamental particles. It was nice when we had 3. In fact, I think everybody really wants to there to be one fundamental particle. That would be the most elegant of all. When we had 3, I think we can accept that maybe nature has 3 fundamental particles when we have 6 and 6 is 12. Plus the 4 carriers, and then there is antiparticles, and there is all the different colors of the quarks. It's starting to look like that there is an awful lot of the fundamental particles, and it's a perfectly legitimate question to ask. How many fundamental particles can you have before you start to wonder if there is some explanation, some deeper story? And that's an idea that I want to revisit. We don't know the answer to that. Right now, it looks like we have a very beautiful, very consistent mathematical theory. It describes all the subatomic data very well, and so it's kind of just a feeling, a thought that some people have that maybe we might be able to go further beyond the standard model someday. Wow, thank you!